Welcome to our next video in the series on condensed matter theory. In this lecture I want to talk about Kohn Sham orbitals and how we can use them to improve the calculation of the kinetic energy within density functional theory. So we have seen that we can calculate the potential energy completely from the density, that the Coulomb repulsion we at least can do the direct term. We still have to talk about the exchange. But the kinetic energy is pretty hard to calculate just from the density alone, because we do not have good representations how the density relates to the kinetic energy of a system. We have no wavelengths anymore. So what we can do is we can define a set of one particle wave functions, psi t of r, that represent quasi-particles. It's very important to realize that these are not the exact electrons that are represented by these wave functions, but some quasi-particle that we can talk about and that we can still calculate with. With this set of quasi-particles we can define the density exact as a sum over the set of occupied quasi-particle states psi tau of r, psi tau of r. And this is the exact density. This is by definition the exact density. And we have defined our one particle wave functions such that this is exact. And of course there are still many ways to define those. And we want an orthonormal set. So from this, the potential energy can be calculated exactly because we have a density, but we can also calculate the kinetic energy, which is a sum over all occupied states, psi tau of r minus h bar squared over 2m gradient square psi tau of r. Now, as we said before, if these represent electrons, this would be the correct kinetic energy. But if these represent electrons, this is not an exact definition, because for an electronic system we cannot write down the ground state wave function in terms of a single Slater determinant. So we can't have both at the same time to be exact. So in order to make the kinetic energy exact, we still have to add a correction to it, and that is what we call the correlation energy of the kinetic energy. And at this point we are exact, and you can very simply show that you're exact. If this is the exact kinetic energy, then T correlation is the exact kinetic energy minus the kinetic energy that you calculate as if these quasi-particles were electrons with a mass m. So it's an absolutely trivial statement that this is exact, because we have added a functional that we can give any value we like. And let me first also define the Coulomb energy in the same way as we did for the Thomas Fermi theory. But we do want something that is exact. And this is the direct Coulomb energy. What is missing is the exchange. And this is the direct Coulomb energy if we would assume that these densities are not influenced by correlations. So we also have a correlation correction here. So in order to find an exact representation, we now have to look at the T correlation and U exchange correlation and see what those are in order to calculate the correct energy or find the correct functional. So far we are still exact, But finding exact representations of T correlation and U exchange correlation is not possible in ways that are useful. As we've seen before, it's not so difficult to define exact functionals that are completely unuseful because you have to go through an intermediate step where you have the full wave functions. And we want here something that works on the density directly. Now, we can simplify the question a little bit, because in principle your functionals can be functions not only of the density at one position but the densities at different positions. As here it is an integral over the density at position r and r prime. So it's not a local functional, but we can always write it as a local functional. So we're going to define the small u exchange correlation and small t correlation as the correlation, the kinetic correlation energy density and Coulomb exchange correlation energy density. And our full exchange correlation energy is given as the integral of the exchange correlation energy density, and the correlation energy for the kinetic energy is given as an integral over the correlation energy density. This is just still an arbitrary exact definition, as this can be any function as long as this is given. So in order now to make this local, we're going to make a Taylor expansion of the density. Such that we can define rho at different positions by the function and the derivative of the density. So we know that rho at the point r prime is given by, at the point r, is given by rho at the point r prime plus, and let me define delta of r as the r minus r prime. So we want to know the density at r, and we're going to give you the density and its derivatives at the point r prime. So it is the gradient of the density at r prime dot the distance plus, and then the second order term, a half delta r dot gradient square of rho of r prime dot delta r plus, and then third order terms. And with that we can calculate the exchange correlation energy density at r prime as the first order, which is a function of the density at point r, plus the second order, which is a function of the gradient of the density in point r prime, plus etc. Such that we now have a functional that only depends on the point in space where you're looking, but then of course not only on the density but all derivatives of the density as well. We can now define approximations. In the local density approximation, we're going to say that U exchange and correlation and T correlation is basically given by only the density local. So U exchange correlation of R is U exchange correlation 1 of the density in R, and GGA, generalized gradient approximation, is going to say that U exchange correlation density in point R is given by U1 exchange correlation of rho of R plus U2 exchange correlation of the gradient of rho of R dot delta R. No, not only. of the derivative in point R. And with that you can in principle calculate the density at different positions if you have an interaction between a local and a non-local density. So now the question still is how to obtain the exchange correlation function for rho of R, or the correlation energy rho of R for the kinetic energy in the LDA, local density approximation. What we can do is we can look at a model system that we can solve exactly. For example, a homogeneous electron gas with interactions, the GGA model. With the use of quantum Monte Carlo methods, we can make approximations of the ground state energy, and we can get reasonable accurate as a function of density. And then we're gonna fit the exchange correlation functional and the kinetic energy correlation functional to these exact solutions, or these numerical exact solutions. You start out by calculating the other properties as a function of the density, and then you see what is missing in the kinetic energy and in the Coulomb energy, and that then defines your additional functionals that you need. Now, of course, you do not have to take the free electron gas or the homogeneous electron gas as a model system. You can also look at other systems. You can look at atoms or lattice models as your model systems, and that allows you to define different functionals. What we have in the end is that we have our exact Hamiltonian, which is a sum pi square over 2m plus a half, I is not j, e square over ri minus rj. I've left out the interaction with the nuclei at the moment, and that then brings you to an LDA Hamiltonian, which is still pi square over 2m plus some effective potential, which is the exchange correlation potential, Ri. The eigenstates of your LDA Hamiltonian now not represent the real particles, but represent some quasi-particles, where the exchange correlation potential does include corrections to the kinetic energy, as the kinetic energy for a single Slater determinant is not the kinetic energy for your real Hamiltonian, such that the densities that you obtain from the LDA Hamiltonian, as well as the total energy obtained for your LDA Hamiltonian, is equal to the density and energy that you obtain in the exact Hamiltonian. These quasi-particles do have physical meaning. If the exchange and correlation energy were zero, they should become the same as the representation of your electrons. And you can actually use them to do physics also for excited states. Of course, then you always have to ask, how accurate is this still, and how much of an approximation do I make? It's no longer exact, but well, it wasn't exact to begin with because we don't know an exact representation for your exchange correlation functionals as a function of density. That all said, density functional theory is by far the most accurate method that we have at the moment to represent real materials, and it is this method that gives you the results that are used normally in condensed matter theory or quantum chemistry. So thank you very much for your attention. We see each other later, and stay healthy.